All right, more SICP. So I had left off around figure 1.4. So basically what we were doing is going through these different ways of doing factorials, and the SICP authors were just illustrating like different ways to go about it and how those look. So, right, so you can describe a rule for computing in factorial by specifying that we first multiply 1 by 2, multiply the result by 3, then by 4, so on. That's straightforward. More formally, we maintain a running product together with a counter that counts up from 1 up to n. Right. So you could see the flow here. So this is the product, this like leftmost column, and this is the counter. So they both start off at 1, and you can see, because we're doing factorial 6, so that stays like, constant. And then, right, and so the way to think about it, so like, okay, so this is counter, this is product, and then counter times product, we multiply these two, and that produces the next product. So we group these two, and then, I have some drawing software that I installed. Let me figure that out. Right, so yeah, this is product on the left, this is counter on the right. And so at each step, you multiply them, and then that product that you get goes to the next step, and then the counter increments, and then multiply again, and the product you get goes to the next step, and the counter increments, and so on, right? So I'll get rid of that. Okay. Right, so they want us to compare the shapes of the two processes that we've considered for figuring out factorials. The n times n minus 1 method over here, and the counter product multiplication method over here. From one point of view, they seem hardly the same at all. Both compute the same mathematical function on the same domain. Each requires the number of steps proportional to n to compute n. Same sequence of multiplications, but the shapes are different. Consider the first process. The substitution reveals a shape of expansion followed by contraction. The expansion occurs as the process builds up a chain of deferred operations, right? 6 times factorial 5, 6 times 5 times factorial 4. So you see, we're not actually doing any of these yet. We keep going down the recursive rabbit hole until we get to the base case. The contraction occurs as the operations are actually performed. So yeah, it expands and then it contracts like a wave. And this type of process, characterized by a chain of deferred operations, is called a recursive process. Carrying out this process requires that the interpreter keep track of the operations to be performed later on. The length of the chain of deferred multiplications, and hence the amount of information needed to keep track of it, grows linearly with n. Such a process is called a linear recursive process. By contrast, the second process does not grow and shrink at each step. all we need to keep track of for any n are the current values of the variables product, counter, and max count. We call this an iterative process. In general, an iterative process is one whose state can be summarized by a fixed number of state variables, together with a fixed rule that describes how the state variables should be updated as the process moves from state to state, and an optional end test that specifies conditions under which the process should terminate. In computing n factorial, the number of the number of steps required grows linearly with n. Such a process is called a linear iterative process. The contrast between the two processes can be seen another way. In the iterative case, the program variables provide a complete description of the state of the process at any point. If we stop the computation between steps, all we would need to do to resume the computation is to supply the interpreter with the values of the three program variables. Not so with the recursive process. In this case, there is some additional hidden information maintained by the interpreter and not contained in the program variables, which indicates where the process is in negotiating the chain of deferred operations. The longer the chain, the more information must be maintained. Right, so you can see here, like, the chain gets pretty long, and then you've got like all these operations that you need to perform still when you get in, and then also you're calling factorial on one. Like this is the peak of the wave, right? This oops. Right. Right. So that's like the peak of it, when you have like the max information. Whereas at any given point here, you've only got the product, the counter, and the max count. That's it. You know, it doesn't matter whether you're at the first step or the final step, or exactly in the middle. You're always at, you always have three things to keep track of. Whereas here, like how many got? Well, I mean, let's think of it. We'll keep each group of, I'll treat each group of like an operation or procedure call and a value as like a thing to keep track of, maybe. So it's like, we got 1, 2, 3, 4, 5. So you're doing like 6 things. So that's a lot. Right. So yeah, it's talking about iterative process. Iterative process is one whose state can be summarized by a fixed number of state variables together with a fixed rule to describe how the state should be updated. Such a process is called linear iterative process. So that's this one. That's figure 1.4 factorial representation. Right. So in contrasting iteration and recursion, we must be careful not to confuse the notion of a recursive process with the notion of a recursive procedure. Yeah, I was confused about this, and I'm glad, because I'm like, wait. So they're saying that this one is a linear recursive process, and this one is linear iterative, but this one has a procedure that calls itself. So I was like, oh, is because I was calling this recursive, like they're calling this a recursive call. So let's see what they say. When we describe a procedure as recursive, we're referring to the syntactic fact that the procedure definition refers either directly or indirectly to the procedure itself. Okay. But when we describe a process following a pattern that is, say, linearly recursive, we're speaking about how the process evolves, not about the syntax of how a procedure is written. Could you have a linearly recursive process that didn't have a recursive call? Question mark. Maybe they'll say, it may seem disturbing. they call things disturbing sometimes in this book, that we refer to a recursive procedure such as fact iter as generating an iterative process. Well, I was disturbed by it, or I was at least, I don't know if I was disturbed, but I was at least surprised and inquiring about that. However, the process really is iterative. Its state is captured completely by its 3 state variables, and an interpreter needed to keep track of only 3 variables in order to execute the process. One reason that the distinction between process and procedure may be confusing is that most implementations of common languages, including Ada, Pascal, and C, this dates itself, are designed in such a way that the interpretation of any recursive procedure consumes an amount of memory that grows with the number of procedure calls, even when the process described is in principle iterative. Okay, let's read that again. One reason that the distinction between process and procedure may be confusing is that most implementations of common languages are designed in such a way that the interpretation of any recursive procedure consumes an amount of memory that grows with the number of procedure calls, even when the process described is in principle iterative. Okay, so most common languages are designed such that if you have they interpret something like a recursive procedure, such as the figure 1.4 procedure with max count, etc. They interpret, which is in fact or in principle iterative. They interpret those types of procedures in such a way that the memory grows with the number of procedure calls. And that fact might be confusing. I guess it would be confusing because that's what you would, like, it's maybe a similar memory growth pattern to the figure 1.3 procedure for figuring out factorial. And so maybe because the memory usage pattern looks the same, you figure that the process is the same. That's my best interpretation of this. As a consequence, these languages can describe iterative processes only by resorting to special purpose looping constructs. So, reading this and thinking about it a bit, Googling some stuff. So when this says, as a result, these, meaning common languages, can describe iterative processes only by resorting to special purpose looping constructs. Describe iterative processes is something that I was getting a little hung up on, and I guess it means like represent as an iterative process in like memory or internally, because it could be like you could have described what the SICP people call a linear iterative process, which again is different than like there's the process procedure distinction, but like you could describe something in your code that would be what they would call a linear iterative process, but because it has a recursive call, common languages will deal with it in a recursive kind of way. And so if you want your programming language to deal with something in an iterative kind of way, you have to use special purpose constructs. But Scheme, or at least the implementation that we'll consider in Chapter 5, does not have this problem. They say it will execute an iterative process in constant space even if the iterative process is described by a recursive procedure. So that's an advantage of this version of Scheme that we're considering. An implementation with this property is called tail recursive. With a tail recursive implementation, iteration can be expressed using the ordinary procedure call mechanism, so that special iteration constructs are useful only as syntactic sugar. By the way, you may have noticed, but I've popped up Simply Scheme, or I popped up a PDF over here of Simply Scheme. I downloaded Simply Scheme's like publicly, it's like free for personal use anyway. So I went to Brian Harvey's website, and he's got this directory here. There's a few books in here by chapter that I used a Chrome extension, and I filtered for the Simply Scheme ones, downloaded them, and bundled them up in PDF Sam, which is a Mac app. So it's super easy to know, because PDFs are good, and it's useful to just like have it as opposed to like having to search on the site if I want to find something. Although I'm going okay through SICP so far, although we'll see. Now we have another exercise, so maybe I'll hit the wall again. I need to switch to easy mode. Okay. So each of the following two procedures defines a method for adding two positive integers in terms of the procedures I and C, which increments its argument by 1, and D easy, which decrements, right? Its argument by 1. Increment, decrement. Yeah, that sounds right.
Decrement. Decrement.
Yeah, okay. So, using a substitution model, illustrate the process generated by each procedure and evaluating for the sum of 4 and 5. Are these processes iterative or recursive? No detour here. Realize that inc and dec are not procedures that are defined in the version of Scheme that I was using in Dr. Racket. So I figured I should actually get an SICP version of Scheme, and I found a link about how to set that up in Dr. Racket, and it was really, really easy and seems to work fine. I got it to pass the appropriate tests. You see I generated this cool square. So I'm going to send that to FI because I know there's other people. There's at least one other person who's working on programming stuff in Scheme. So they may benefit from this knowledge. All right, so now I've set up the correct language, and also I've imported the Racket trace library so that I can run trace. And you see I'm doing that in my definitions. I'm running a trace on plus. And so when I add 3 and 4, we see the result. So what's the structure here? So we have 3 and 4, and then the program says if A is 0, then return B. Otherwise, we call inc and make a recursive call to plus, and we give it the variables. We pass it decremented A and B again. And so basically we keep going down the recursion rabbit hole until A equals 0. So what happens that first time what happens when we hit 0, when A is 0? The plus function will return, or the plus procedure will return B. So when A is 0 over here, then plus will return, out of this stuff, it'll return the B, which will be 4. And then what? It'll get incremented up by 1, because that's what the increment procedure does that we're importing from the SICP basic language library there thing. So we go from 4 to 5, but we did a couple of recursive calls to plus, so we're a couple layers deep. So we had to go we had to decrement down 3 steps and go through like 3 levels of recursion to get down to where A is 0. So then we've got to go up 3 steps until we're done making, all the calls and doing all the upward increments that we need to do. Because remember, as we were going through this process, it was like, okay, if A is 0, then B. If not, then increment and recursive call, decrement A and B. And then the same process again. So we decremented A from 3 to 2, and then we went through the whole thing again, and from 2 to 1, and from 1 to 0. So now we've got to percolate back up the recursion tree. And eventually we do that, and we wind up with a case where A is 0 and B is 7. And I'm going to say that this is a recursive process, to be precise about the language that SICP is using, because we need to, you could, I think maybe you could see just the flow of it visually, but also we need to keep track, or the interpreter needs to keep track of how many layers deep we are in recursive calls. Like that's vital information. I don't think you could just take the A and the B and figure out where you were in the process and carry on from there. Like you need the information of the state of the program. Like, yeah, so I was, you couldn't just look at the A and the B and figure out like where you were. Like, what did it say about that? Right. In the iterative case, the program variables provide a complete description of the state of the process at any point. If we stop the computation between steps, all we would need to do to resume the computation is to supply the interpreter with the values of the 3 program variables. Not so with the recursive process. In this case, there is some additional hidden information maintained by the interpreter and not contained in the program variables, which indicates where the process is in negotiating the chain of deferred operations. I want to really tie it down concretely. The deferred operations here are the incrementing. Like you see how that all happens at the end? Like the decrementing happens all in one step, but the incrementing happens at the very end. It's kind of like yeah, all the multiplying here. Figure 1.3. Whoa, that mouse cursor is getting huge. It's weird. What was up with that? Oh, there it goes again. Oh. Whoa, how big can I make it? Okay. It's enough. It's enough fun with the mouse. It was just very surprising. It's like, well, I get as big as my head. Okay. So, right. So now let's try this one. So yeah, you can just see visually the difference. Like I'm gonna try and talk it out, but like it's like, yeah, obvious answer is obvious. I mean, not really obvious, but like, yeah, there's an FI discussion about something like that, about easy. Something is easy to you once you know all the stuff. Anyway, that's a tangent. I'm gonna cut that tangent off. Okay. So you can just tell right away. Like, yeah, there's a recursive procedural call, but like at each step you have a completed phase of the program, right? So like there's nothing being put off till later. You know? Like we do the sum of 3 and 4. And so step 1 is we decrement A and increment B. So 2 and 5, right? And when we do that, that's done, that's finished. That whole phase of the program, you know, is done. And if you like they say in the text, if you stopped it here, and you said, you know, if computers were like a lot slower than they are, and you stopped, or this was a more difficult thing than it was, and you stopped it here, and what you had was, you know, these numbers indicating the state of the program, and you knew what you were trying to do, you'd say, okay, well, let's just pick it up from here. This is all we need. So this is what they're calling iterative. Let's look at exercise 1.10. The following procedure computes a mathematical function called Ackermann's function. define AXY. All right. So they asked for some values for this, for this procedure, for these expressions. So I plopped that in. That was pretty straightforward. Now it says, now this is going to be the hard part. Consider the following procedures where A is the procedure defined above. And then it's giving us some procedures, and these procedures are calling this Ackermann's function procedure. And it says, give concise mathematical definitions for the functions computed by the procedures f, g, and h for positive integer values of n. For example, kn computes 5n squared. So I'm a little intimidated by this, but that's okay. We'll see if I can figure out how to. Let me start with the one that they give, and we're trying to work backwards from that. What they give it's not even calling the Ackermann function. It's just like multiplying. All right, so I think this is easier than I initially thought. So we just have to basically look at this, figure out which cond applies, and then like kind of plug stuff in. So for function fn, f of n, calling the Ackermann function with 0, which is going to be x up here, and n, which is going to be y over here. So if x is 0, what do we do? Well, it tells us. We multiply, we get the product of 2 and y. So what's the product? So what is y? N. What's the product of 2 and n? 2n. Pretty straightforward. I think that fulfills the decree of concise mathematical definition. It was a mandate. I think mandate's better than decree. And so x is g. X is equal to 1. That's not. I'm not gonna look at the else yet. I'll look at that if all else fails. So x equals to 1 is equal to 1 is not here. Y equal to n isn't here, so then we do have to look at the else. So what's going to happen? We're going to make a recursive call to the Ackermann function. The recursive call is going to pass x minus 1 as the new x, and so hang on. So x minus 1 is going to be the new x, and the new y. So you see, the y is going to be this whole thing, right? Now, why this? Because, oh, I erred, actually. There we go. Because it says the Ackermann function of x, which here is still 1, and n minus 1. So you can see for this recursive call to the Ackermann procedure, for the what's going to be the new x, we don't have to do anything else, like we'd say, because we know what x is. X starts at 1 from here, and then we just reduce it by 1 and we pass it recursively, and so that's done. But for what's going to be the recursively called y, we need to do another step. We need to go another level deep. And so you see this recursive call is going to use the current x, which is 1, and then y minus 1, which will be n minus 1. And this x and this y don't hit on any of our conditions. Then we go to another nested recursive call in the else. I decided this is an inadequate way to represent this, so give me a minute. I actually tried seeing if I could figure out a good way to make like a diagram or something to show the recursion, but it seemed like it was going to be harder than I thought it was, so I am going to try and do it in text. All right, so I'm a little stuck at the moment and about due for a activity change anyway, but just to summarize where I'm at. So I basically tried like mentally stepping through the procedure. Like if we gave 1 and n to the Ackermann function, and like what would happen at different steps. And it seemed like cause so the first step, the f n function, that resolved really easily because we had x equals 0, so that was straightforward. But because with this with G we have the recursive call, it seems like it doesn't. So like if y was a number, then at some point, if y was a positive number, at some point it would hit 1, and then the thing would end. But the way it was playing out, it was like it's getting n minus 1 and n minus 2, and so like it seemed like from that, like that way of doing it, that I wasn't gonna be able to figure it out. So then I was thinking, well, there must be, like, I must be approaching the problem in a fundamentally mistaken way, in terms of how I am supposed to be thinking about it. There must be like maybe like a more mathematical approach. Like I'm trying to look at it programmatically, but maybe I'm supposed to look at it more mathy. But I'm having trouble seeing what that is right now. I'm gonna take a little break and end the video, and if somebody wants to give me a hint, that would be useful, including, by the way, just like a whole, like if the hint is review the basics of mathematical functions, that's okay. That's a hint. But if it's more tailored, that's good too. Okay, so I'm gonna end the video here. Maybe do some Ruby on Rails stuff.